Good morning, guys. I apologize for you needing to see a second video of titration list, but hopefully this will go a little bit better than this. So I'm going to go ahead and get started. I'm going to share my screen. So again, today we're talking about titration and Lewis. This is lecture 5 for Chem 111. So hopefully you guys are with me. This is chapter 15, sections 8, 9, 10, and 12, and chapter 16, sections 4 and 5. So today we're going to talk about diprotic and polyprotic acids. So definition, more than one acidic proton, it has two, that's diprotic. So H2CO3 has two acid protons, diprotic acid. H3PO4 has three acidic protons, and therefore it's triprotic. What happens when we look at these things, we talk about H2CO3, H2CO3 can come apart to become H plus and HCO3 minus. But that HCO3 can also then come apart to become H plus and CO3 2 minus. So that is a two-step process. The overall process is H2CO3 going to 2H plus CO3 2 minus. We can talk about that as the overall process, or the two-step process. For the three protons, it's the three-step process. Each successive proton that we take off is a weaker acid. And all the same rules apply that applied before. The same things are going to happen when we talk about diprotic and polyprotic acids, as happened when we talked about the monoprotic. Okay? So the next example is actually from your textbook. This is oxalic acid. This is example 15.11. And what happens is we're looking at oxalic acid, H2C2O4, going to H plus HC2O4 minus. Initially, we have a concentration of H2C2O4 of 0.1 molar. We don't have any H plus, or at least none at one time, and we don't have any of the anion. We know that the change for that is going to be negative X for our reactant and plus X for our products. And then at equilibrium, we're going to be looking at 0.10 minus X. We always start by assuming that X is small compared to the 0.10, but in this case it is not. So once we get that X, we can compare that X value to the 0.10. And if it's less than 5%, we can use that assumption. In this case, we cannot do that. And so we have to use the quadratic equation to solve for this. That then gives us x squared plus 6.5 times 10 to the minus 2x minus 6.5 times 10 to the minus 3 equals 0. When the equilibrium for the first stage of ionization is reached, concentrations are then H plus is 0.054. HC2O4 minus is 0.054, and the H2C2OH equals the 0.10 minus the 0.054, which is 0.06 mole. So yay, we've reached equilibrium there. We found all of our concentrations in the exact same way that we've done. And if you need a walkthrough on that, that's in the example of the text. I didn't present it here because you've already cut the full presentation. In the second stage, though, that HC2OH4 minus, which has a concentration of 0.054, can also react to give us that H plus the C2O4 2 minus. That, in this case, we're going to list it as a minus Y and a plus Y just to avoid confusion. That's all it is. We can use X here too, and I tend to do that, so it's one of the reasons that I'm mentioning it. We can apply that approximation. In this case, we can do it, and it is smaller than the 5%, which we see there. So we apply the approximation. That gives us the 0.05 plus Y is approximately 0.05, and 0.05 minus Y is approximately 0.054. We obtain 0.054 times Y divided by 0.054. Okay. And again, that's because our HC2OH minus and our H plus from the last equilibrium were equal. So that means that we're then looking at Y being equal to the Ka for that second ionization. That should be in your exam handouts now. There is a Ka table that should be there. And if it's not in the Ka table there, then it has to be given to you. So there should be a table of Ka values for weak acids in that place. And also for the diproducts. So this will probably may be in both. So that's how you get that 6.1 times 10 to the minus 5th. You can test your approximation, which they've done here, and because it's less than 5%, we can use it. That means that we now have equilibrium concentrations for all of these species. So our starting material, H2C2O4, is 0.046 molar. Our HC2OH4 minus is the 0.054 molar. The H plus comes out to be 0.054 molar. The C2H4 2 minus is 6.1 times 10 to the minus 5th. And of course our OH minus, based on our H plus concentration, is 1.9 times 10 to the minus 13th. Okay, so that is the same kind of thing that we've been talking about all of this time. It's just a slightly longer process. We go through the first equilibrium. The results of that first equilibrium then go into the second ice table. And then that second ice table is used to do the calculations from there. Like I said, your Ka values are either going to be given to you on a test or they're going to be in the reference materials that you have. Notice, please, that I had to make a change to the exam handouts. I need to make an announcement about this. The initial exam handouts you got were supposed to contain 2 tables that they did not. And that was the Kas for the weak acids and the weak bases. Those are now in there. So there may be some data that you're looking at for the practices that you didn't know where those Ks came from. That's why. So that's what we're talking about for that. Questions, comments, problems on our oxalic acid example. If you have some, go ahead and take a look at the example in the textbook. It's available in the ebook on Alex. So you can go to the 3 little horizontal lines in the upper left corner. Click that. You'll click the textbook, and that's going to show you the ebook. And you'll find this in section 15. It's example 15. Okay. Now, when we talk about polyprotic acids, they have more than one acidic proton. Again, as I said before, it's always easier to remove the first proton than any successive proton. It's going to be more stable when we take the first one off than it is when we take the second one. If the factor in the Ka values for the first and second dissociation has a difference of 3 or greater, the pH generally depends only on the first dissociation. So that's typically what we're talking about. And here's our table, so we can look at some of those values. And that's a table from a different textbook, but the one that's included in your exam handouts is the one from strong versus weak acids. Oh dear Lord. So we've talked about strong acids and weak acids a little bit. We talked about the fact that strong acids are molecules where it's favorable to have the anion on its own. It's a more stable anion. So, and the more stable that anion is, the stronger the acid, because it's easy to yank that proton off if it's a stable anion. So a strong acid is going to have our H3O plus concentration at equilibrium equal to the HA at the initial, because all of it reacts. That reaction is complete and it only gives us products, and therefore the Ka for that is undefined. So they are equal to each other. For weak acid, that's not going to be the case. Not all of our acid is going to dissociate, and so our H3O plus is not going to be equal to our concentration of HA. We need to use the Ka for that equilibrium to determine what that concentration is going to be. Now, think about it for a second. The higher number of ions I have in solution, the greater the ionization of those materials, then I'm going to have greater conductivity. Okay, so more ions, more conductivity. That is something that you need to be able to think about when we start talking about some of these complex equilibria. Right? Questions, comments, problems? Hopefully not. You know the procedure. If you have some, please let me know. Send me an email. Tell me what's going on. We'll see what we can do. Now, there are a couple of different types of acids that we need to be able to talk about. So you may be asked to provide a hydrohalic acid, which is something like HCl, HBr, HI. So an H attached to a halogen is really what we're looking at. Remember, however, that HF is not a hydrohalic acid, and that's because HF is not a strong acid. Therefore, it is not included in this. Okay. Generally speaking, the Cl minus, the Br minus, and the I minus are very happy being alone, so these are very strong acids. Okay. We also have oxo acids. They contain an H, an O, and some other atom, some Z. So Z can be something like a CH3 group, something like that. Anything that will attach to the O and the H. Now, if Z is highly electronegative or in a high oxidation state, it attracts the electrons, and then it's a strong acid. We can do comparisons for different central atoms from the same group. So higher electronegativity will be the stronger acid. So again, if we're looking at our halogens, let's just say that we're talking about rather than a CH3 group, we had a CCl3 attached to that OH, right? That's going to be more electronegative than, say, looking at an OHCBr3, because this the Cl is more electronegative and therefore it's a better acid. Okay. We can also talk about the same central atoms, but different numbers of attached groups. The longer that chain is, the more stable it's going to be, the more ability it has to handle that charge. Okay. So those are our oxo acids. We also talk about carboxylic acids. Carboxylic acids have the structure shown. So we have some, again some R groups. CH3 is a pretty common one. Alkanes are fairly common there. The nature of the R group determines what type of acid it is. If the R group is going to make the anion more stable, then the acid will form. This is used for comparison only. So you may get asked, okay, of these three acids, which is the best? And that's going to be based on what is the nature of the R group. How well is it going to be able to handle that electronegativity? Now, is this something that happens and something that gets talked about in chemistry? Absolutely. Is it something we're going to talk about in great detail here? No. No, I'm not going to ask you to compare those acids, but I am going to ask you things like identify a hydrohalic acid. What would you call this acid? Those kinds of things. I think that comparisons are best left for organic chemistry, where we start talking about what are the nature of those functional groups, and therefore we're better able to understand what it is we're looking at there. So that is not something we talk about in great detail for this class. Again, the expectation on the test is that you be able to identify a hydrohalic acid, say this is a hydrohalic acid, or give me an example of a hydrohalic acid. Same is going to be true for the oxo acids and the carboxylic acids. So you should be able to draw me a general structure, and the way that they've drawn these is perfectly fine. So you could say, when you look at this, if you're talking about the oxo acids, that it's a ZOH. That works. And that's all we're really looking for. Now, I may ask you, what is the nature of that what could Z be? And that's entirely up to you for what you could put there. So some examples will exist in the Ka tables that you have, so you can look there for examples. Okay? Questions, comments, problems? Let's talk about our salts. Now that we know that we have strong acids and weak acids, if I have a weak acid, it's not completely ionized, right? But I do have some of that ion there. The problem that I have once I have that ion there is that it can act as a base and pick up a proton from anything that's around. So that's what we're talking about when we talk about these salts. There are three cases that we're going to consider. A neutral salt is where we have the conjugate base and conjugate acid of a strong acid and a strong base. Okay. So since the conjugates of the strong acid and the strong base are going to be weak, they therefore will not react with anything that has protons, and therefore this will stay a neutral solution. We can, on the other hand, have situations where we have acidic salts. These are salts derived from a strong acid and a weak base. Okay, so if I react HCl with NH3, so ammonia, which is a weak base, that NH3 picks up the H plus, becomes NH4 plus, but that NH4 plus isn't overly happy being NH4 plus, and so we can donate that proton again, and so that's an acidic salt. Okay, in the terms of the bases, this is what I was talking about before. Salt from a strong base and a weak acid. The weak acid anion reacts with the water to produce OH minus. So strong base, NaOH, weak acid, HF, is going to give me NaF as my salt. And that F can react with water to produce OH minus. So it's just recognizing that we're looking at the conjugate base of a strong or weak acid. So it's the conjugate base of a weak acid, or the conjugate acid of weak base. Confused myself, sorry. But that's what we're talking about. So those are the kinds of things that you need to be able to know. What impact does this really have on you? It's a lot of information. What do you care? Okay. I need you to be able to look at a salt and tell me, is this a neutral salt? Is this an acidic salt? Is this a basic salt? So identify what it's going to do when it gets in contact with water. Is there going to be a reaction there? And what is it going to be? The other thing I'm going to need you to be able to do is if I say I need to make a solution from a salt that is acidic, name me. I need to make a solution from a salt that is basic, name me one. Okay, so you need to be able to provide those kinds of examples. Hopefully that makes sense. If it does not, please let me know. So what's next? Well, let's change gears a little bit and talk about Lewis acids and bases. Lewis acids and bases. As we mentioned last time, Lewis acids and bases have nothing to do with proton donation or production of OH minus, or in Lewis definitions. A Lewis acid accepts a pair of electrons, and a Lewis base donates a pair of electrons. Now, I'll show you what that looks like in just a minute. But that's our definition for Lewis. All right, remember that I gave you a table in the last lecture about how we define the different types of acids and bases. So that is something you're going to have to be able to reference. So you need to be able to look at this thing and say, okay, that's an acid because, or that's a base because. What is it about that particular compound that makes it an acid or base? And again, we're looking at things like acids being proton donors, acids being electron acceptors, bases being either proton acceptors, OH minus producers, or donation of a pair of electrons. So questions about that? Hopefully not. Calculations. So we can use pH to calculate Ka. The pH of a 0.1 molar solution of formic acid, HCOOH at 25 degrees, is 2.38. Calculate Ka for formic acid at this temperature. So my pH is 2.38. That means that my H3O plus is 10 to the negative 2.38, because I have to take 10 to the negative pH. That gives me 4.169 times 10 to the minus 3. Now, X is tiny, right? So we're looking at a situation where our initial HCOOH, our initial HCOOH is 0.1 molar. Our change is in minus X for that, and we're looking at generating a plus X for the H plus and a plus X for the HCOO minus. Now, that value of H plus is tiny, okay? So we know that that's less than the 5% of the initial that we started. Now I can do this subtraction, and that's what I've shown here, is the 0.0958313. Simplifies the calculation, but that gives me all of the concentrations that I need in that table. So since it's effectively given me X to start, and I know that the X for the H plus has to be the same as the X for the HCOO minus. So then I have two of those values, and the only thing I have to consider is, based on that pH, how much of that acid is associated, and therefore what value do I have from that. So that's how we do calculations from concentration of an acid and a pH that's given to us. We can then calculate Ka from those things. Okay. My Ka value is going to be equal to that the H3O plus concentration squared divided by the equilibrium concentration of HCOOH. So again, we can calculate that Ka. The method to follow, we write the equilibrium expression for the ionization equilibrium. We write the equilibrium constant expression. Set up an ice table and substitute equilibrium concentrations into the equilibrium constant expression and solve for X. So let's calculate the pH of a 0.3 molar solution of acetic acid, HC2H3O2, 25 degrees. So our reaction for this is HC2H3O2 plus H2O. It gives me an H3O plus C2H3O2 minus. I know that that value is 1.85 times 10 to the minus fifth, and I get that from my weak acid Ka table. So I have my initial row as 0.30 for the acid. I have 0 for the H plus and 0 for the anion. My change is negative X for the acid, plus X and plus X for the H plus and the anion. My equilibrium is then going to be equal to the values that we're about to calculate. And we initially make the assumption that the 0.30, the X is going to be negligible compared to that. So I'm going to multiply my Ka times the initial concentration of the acid. That gives me 5.55 times 10 to the minus 6. And that's equal to X squared. I take the square root of that. That gives me 2.4 times 10 to the minus 3. That is the concentration of H plus, H3O plus. So my pH is the negative log of that value, which gives me a value of 2.6. So X is very small. We can look, now that we've got an X, we can compare that to what our initial value was, and it's 0.79%. So we can, that's awesome. It doesn't always work that way, but hopefully it works that way most of the time because it makes things simpler and a lot faster. We can also use the pH to calculate Kb. So let's take a look at that. So the pH of a 0.10 molar solution of ammonia, NH3 at 25 degrees, is 11.13. Calculate Kb for ammonia at this temperature. So my Kb is going to be equal to my product, so my reactant. So my NH3, it reacts with the H2O, which is a liquid. It gives me NH4 plus OH minus. So that's how I get my Kb equal to the concentration of NH4 plus times the concentration of OH minus divided by the concentration of NH3. So that's my Kb expression. In my ice table, I have NH3 as 0.1. Initially, I have no NH4 plus or OH minus. Again, I have my base minus the X. I have my conjugate acid as plus X, and my OH minus is plus X. And then we solve for our equilibrium. Since I have a pH, right, I can take my pH and subtract that from 14 to give me a pOH, which is 2.87. My OH minus concentration is then going to be equal to 10 to the negative 2.87. Right? 10 to the negative pOH gives me OH minus. And that's 0.0013. That's my X value. I can compare that to the 0.1 that I started with. That is small, 1.3%, so that's a valid assumption. And that means that my concentration for the NH4 plus is 1.3 times 10 minus 3. Okay. And again, all I've done is I left the OH minus as 10 to the negative 14th divided by 10 to the negative 11.13. That's another way to arrive at that OH plus value. It's another way. And that then gives me my equilibrium as 9.9 times 10 minus 2. Okay. So questions, comments, problems about that? Hopefully we're good about that. So that's using pH to calculate Kb. Oh Lord, we're going to talk about titration. We need to talk about titration. What is titration? Well, you're going to do lots of titration. If you're in a physical lab, you would be expected to do these titrations. You do a standardization and then an actual titration. Typically, those would be done on the same day. Here, we don't have time for that. So that doesn't happen that way. And we always do our titrations when we set them up in this way multiple times. Because what happens, inevitably, the first time you do it, you blow right past the end, and then you have to go back and do it again. So then it's sort of kind of where it is, and so we always set it up such that it's not a big deal, and we can do it more than once. We always do it at least 3 times so that we get an average of those values, because that is the best way for us to get. Now let's take a look at what we have here. We have a burette that's filled with a solution of known concentration. This is NaOH. So we have a standardized NaOH solution here. I'll talk about the standardization in a bit. That standardized solution is used to then titrate an unknown acid. Okay, so either we don't know what the acid is, or we don't know what the concentration is, or both. It could be either, or both of them. So we have this solution of that acid. I know how much of it there is. I don't know what its concentration is. That's in this beaker. And then I use a pH meter to measure the change in pH. So we're going to keep adding that base very slowly until the pH gets to near 7. Because I know that's where, that's sort of what we're looking for. Now, it's not always going to be 7. When we do a strong acid and a strong base, it's going to be 7. It's not always the case. What happens when we get to a point where the concentration, the moles of acid, is equal to the moles of base, then I'm in a situation that looks just like Kw. So my pH should be 7 for that. Okay. Again, right here we're talking about strong acids and strong bases. So if that's the case, we're not going to have a salt that's interfering with that. That will be our equivalence. So that's when the stoichiometric amount of acid equals that of the base. And that's in terms of moles of acid and base as opposed to molarity. We aren't looking at molarity here because the volume is changing every time I add something to it. So we don't worry about that here. To make it simpler for us, we worry about just doing it in terms of moles. Okay. So like I said, the initial case that we're talking about is strong acid with a strong base. In the start of the titration, to near the equivalence point, pH goes up very slowly. So we start with a strong acid, pH is low, pH goes up very, very slowly in the first region. Just before the equivalence point, all of a sudden the pH goes nuts, and we get this huge change from a little tiny amount of that base, right? And that's because we've now gone from a situation where that addition of the base is being reacted with the acid that's already present. So we go from there to there's no more acid, and all of a sudden we have all this excess OH minus in this solution. So that's what we're talking about. At the equivalence point for a strong acid and a strong base, the pH is 7. As we continue to add more base, the pH again levels off. So I was talking about we blow past the equivalence point. Well, that's what I'm talking about. It happens really, really fast. And we're talking partial drops on a burette to make this happen. Okay. There are things we're going to talk about in terms of what's important to know how where that is and how we measure all of that. So that's what we're going to be talking about now, as well as what do these titration curves look like when we're not talking about strong acid and strong base. Okay. So a strong base with a strong acid is almost exactly the same. It's just reversed. It's flipped. So instead of starting with low pH and going to high, we're going to starting with high pH and going to low. But nothing else is different. We start with a high pH solution, we reach pH 7 at the equivalence point, and then low pH at the end. So we've flipped from what we were doing just a minute ago. Cool. Now if we talk about the titration of a weak acid with a strong base, we're going to have to figure out how to make some of those calculations. So we need to find the Ka to find the initial pH. So that's before we add any acid to it, or any base to it. We're going to find the pH in the buffer region using the stoichiometry followed by the Henderson-Hasselbalch equation. So what do I mean by the buffer region? Well, as I add a strong base to the acid, I generate the anion of the weak acid. Once I have that acid and its anion in the same solution, now I have a buffer. And so I have to consider that buffer region by using Henderson-Hasselbalch. That buffer region doesn't last forever, but we do have it as long as we have both the anion present and the weak acid. At the equivalence point, the pH is greater than 7. And that's because we have that F minus, if we were talking about HF, and that's why I said that, sorry. But our anion reacting with the water to become the acid again, so back to HA, and that leaves me with OH minus. So my pH at the equivalence point is going to be higher than 7. As more base is added, the pH levels off. So you'll see the same form of titration as what we talked about in previous slides, but now our pH is, our equivalence point pH has slid up. Okay. That should be everything that I need to talk about there. I missed something. Ways that a weak acid titration differs from a strong acid titration. So you'll see a number of curves over here. We have Ka equals 10 to the negative 8, negative 6, negative 4, negative 2. And then this last one is a strong acid. So as we look at the curves going down, we're becoming stronger acids. That means we have a higher initial concentration, we have less region, or we stay here in this high acid concentration until we can make this huge change. When I'm talking about a weak acid, it's not as big of a change. Okay, so that's kind of what you might be looking at. Now, why is that relevant? Because you might get asked, what does that mean? Which of these is a stronger acid? You might see curves that are actually labeled as different acids and might get asked which is the strongest acid and how do you know? Again, the pH change near the equivalence point is smaller for a weak acid, and that's largely due to that buffer region. And the pH of the equivalence point is greater than 7 for a weak acid. So not only has our equivalence point become a narrower region, but it's also shifted up in pH. So those are things that you can do to compare those titration curves and things that we might ask you to do. When we talk about titration of polyprotic acids, so we know that an acid titration starts at a low pH. We then get it to an equivalence point where we change pH very rapidly, and then we flatten out as we continue to add more base. Well, I know that once I've done that first proton, that's my strong acid in that case, then I have a second proton that I can deal with. And so what effectively happens is that we have two weak acid titrations on top of each other. So that region that we reach, the pH, after we pull off that first acidic proton, is going to be higher than what we had with the second proton than it was with the first. And we're going to see the same sorts of characteristics in both of those. Okay. You can look at this and say, all right, I know that in this particular place on this graph, so right at the beginning, all I have is my polyprotic acid. Right? When I get to that point where I hit the first equivalence point, then almost everything that I have is that H2PO3 minus. So that's my dominant species. And then when I get to the second equivalence point, we're talking about the dominant species being HPO3 2 minus. Okay. We can use the Henderson-Hasselbalch equation. We can see that the halfway to each equivalence point gives us the Ka for that step. So if I look at the region, let me see. If we look at this region right here, so if I look at this region right here, this is what I call my buffer region. That is a buffer region, so it is dictated, or pH is dictated by the Henderson-Hasselbalch. When we get to the halfway to the equivalence point, now I've taken this acid that I had initially, and I've reacted half of it to become the anion. That means that the concentration of that weak acid and the concentration of the anion are equal. If those two are equal, Henderson-Hasselbalch equation says that pH equals pKa. Therefore, I can find the Ka at that half equivalence volume. Now, see, I see my equivalence point is here at 50 mils, right? So we're talking about what is the pH here at the 25 mil mark. That's what I'm concerned about. So that pH is going to be equal to my pKa. All right? So that's how we do that in that particular region. And Same can be done for the second. Questions, comments, problems about that? Sweet. Let's talk about indicators. So there are a couple of ways that we typically do titrations. Actually, there are a couple that we don't talk about, but they're done in industry. One of the ways that we talk about doing this is using a pH reader. So we can see the change in the pH directly by doing that. That is a way that's kind of boring. In my opinion, it's kind of boring. The way that we used to do this before we had pH readers was to use something called an indicator. So what is known about indicators is that they're acid-base combinations. In the acidic form, the molecule has one color, and in the basic form, it has a different color. So if I'm looking to titrate an acid that has an equivalence point before the indicator that I'm looking at, then once I've titrated all of that acid, then I start titrating the indicator, and I start that color change. So it happens after the equivalence point for the first acid. There is a gap for when it happens, depending on how well we've chosen our indicator. And then we see this color change. Right? Obviously, we're looking for a very specific color change, i.e. the first indication of it is what we're looking for. And we want that because that's the least problematic volume addition. So we want to add as little volume as possible past the first equivalence point to get that color change so that we can minimize the error that I see in. We call that a titration error. It's the difference between the equivalence point and the end point, which is what we detect with the indicator. So we can use that, and there are lots of indicators that can be used. You'll see if you're in the physical laboratory that we have some graphs that show you the indicators and where on the pH scale they would be used. You can look that up in a textbook as well, so that if you're trying to look at a particular acid, you can make a choice as to what is the best indicator for that acid. If you don't know what the acid is, it makes it a little more complicated to make that choice, and you may have to do some trial and error to make that. So that choice can be critical. So we were just talking about the fact that we need to make a particular choice. What we see here is that we have an unsatisfactory indicator for titration of a weak base with a strong acid because the color changes before our equivalence. That's not what we want. We don't want to see that color change before we've gotten to the part that we care about. So that doesn't work for us. Suitable indicator for titration of a weak base with a strong acid because the equivalence point falls within the color change. Okay, so chances are we're going to see it exactly where we need to see it. There's a very small titration error that we see in those cases. Right? So that's what we're talking about in terms of color indicator choice and how well that represents our equivalence. Questions, comments, problems on that? Hopefully not. But again, if you do, let me know. And that is everything that we had to talk about. So that gets us through our Lewis-based definitions, some of the salt properties that we need to talk about, some of the diprotic and triprotic acids and how we do those calculations, how we can use the pH to calculate Ka and Kb, and all of our happy titration information and Lewis acids and bases. So hopefully that's a better representation of this lecture for you guys. I apologize for the fact that I have to say it twice. Again, if you have any questions, comments, or problems, please let me know. And I will talk to you guys soon. Thanks.